Alright, so today I'm going to discuss power series. Now, power series are used to figure out more advanced calculus problems, as well as being the basis of Taylor series. Now, Taylor series are used to approximate certain functions. In fact, they are used by calculators to calculate values of said functions. So essentially, power series are the basis of how a calculator calculates. Now, the general form for a power series is the sum from n equals 0 to infinity of c sub n times x minus a to the nth power. Now, I will go through each of these variables individually, starting with x, which is the variable. So, for example, if we have the function e to the x, which actually has relations to power series, the x here is the same as this x here. So this x in the power series, when you work it all out, becomes this x. So it's the variable. Next, we have n, which is the term number in the series. So a series is the sum of a sequence of terms, and n indicates what number in the sequence the term is. So, i.e., it could be the 0th term, or the 1st term, or the 2nd term, all the way up to the infinitieth term. Now, because of this, n has to be an integer. You can't have the 1.7th term. That doesn't make any sense. Now we have a, which is the center. And this will become more relevant when I talk about the convergence of power series. And finally, we have c sub n, which is the coefficient. Now, the coefficient is constant for each term, but can change term to term. So, i.e., our coefficient could equal n. So for the first term, it's 1, the second term it's 2, and for the 37th term, it would be 37. And the coefficient can be other potential values, but they are constant for each term, even though they do vary term to term. Alright, now, because this is a series, one of the things we are most concerned about is convergence. And, because we have a variable in power series, it will converge only for certain values of x. So, there is an interval of x values for which our series converges. Now, our radius of convergence, r, which is half the length of the interval, is greater than the absolute value of x minus a. And a is the center of our interval, which is why we call it the center. Now, what we do is we take a value of x and plug it in here to figure out its distance from the center. And as long as that distance is not greater than our radius of convergence, that value of x will cause our series to converge. Now, the values of r and a vary from series to series. So, it's entirely possible that we'll have a series where it only converges when x is equal to a. On the flip side, it is also entirely possible that it will converge for all values of x. So, i.e., our radius of convergence is equal to infinity. It always converges. Now, this brings up the question of how do we find the radius of convergence? Well, to do that, I need to introduce the ratio test. Now, for the ratio test, we take some nth term, which we write as a sub n, and that is under the following term, or the n plus first term, which we write as a sub n plus 1. Now, next, we take the limit as n approaches infinity of the absolute value of this. So, we find the infinitieth plus 1 term divided by the infinitieth term. Now, if that is less than 1, then our series will converge. However, if it is greater than 1, then our series diverges. But if it equals 1, then the test is inconclusive, and we'll have to use some other test for convergence. Next, we plug our power series in to our ratio test. So what we have is c sub n plus 1 times x minus a to the n plus 1 divided by c sub n times x minus a to the nth. And we are taking the absolute value of this, and because we want our power series to converge, we want to find this when it is less than 1. Now, we can simplify a few things. As a property of exponents, when we are adding exponents, we can rewrite that as x minus a to the nth times x minus a to the first, which is just x minus a. Now, because we have an x minus a to the nth on the bottom and on the top, those can cancel. Now, we also want to move our coefficient ratio to the other side. And to do that, we multiply by the absolute value of the reciprocal. We have to use the absolute value because, we have the absolute value over here. So, now rewriting this out, we have the absolute value of x minus a, which is less than the absolute value of c sub n over c sub n plus 1. Now, we do still need to take these as the limit of n approaches infinity. So, for our coefficient ratio here, we'll take the limit as n approaches infinity of that. Now, we don't need to do it for x minus a because there is no n there. I mean, the limit as n approaches infinity of x minus a is just x minus a. It's pointless to have the limit in there. Now, I would like to point out that we do need to use the general form for our coefficients. We can't use specific values in there for them. So, for example, in my first example with coefficients, where I had c sub n equal n, what we would do for that is we would have the limit as n approaches infinity of the absolute value of n over n plus 1. And because of the way limits work, this would end up equaling 1. Now, you may notice a few similarities between this and our radius of convergence. We have the absolute value of x minus a is less than a term. And in fact, this term is equal to our radius of convergence. So we can write r equals the limit as n approaches infinity of the absolute value of c sub n over c sub n plus 1. And that is how we would find our radius of convergence. Now that we know our radius of convergence and our center, which we can look up in the power series, note that if you don't see anything being subtracted or added to x, then it means that our center is 0. But nevertheless, now that we know our radius of convergence and our center, we can find our interval of convergence. So what we do is we first need to break up this absolute value. And we can do that by showing that the negative radius of convergence is less than x minus a, which in turn is less than the positive radius of convergence. Now, because we want to find the interval for x, we need to get x alone. So we add a to all three sides. So that leaves us with the interval is a minus r to a plus r. Now, this doesn't tell us whether or not the endpoints converge, only that all the terms within this interval do converge. But if we plug in an endpoint into the ratio test, then we get an answer of 1. And if you recall, an answer of 1 is inconclusive. So we need to use some other test to figure out whether or not the endpoints converge or diverge. Most often, these tests are the direct comparison test, the integral test, or the alternating series test. So, to show convergence with a direct comparison test, we will have our test function, t of x, and we need to show that a converging function, f of x, we need to show that our converging function is always greater than our test function. So, for example, if we have the test function 1 over x squared plus 1, we need to show that this is always smaller than 1 over x squared, which is our unknown converging function. Now, we know this because of the plus 1. So, whatever value of x we plug into these two functions, we will get a larger denominator for our test function and a larger denominator means a smaller function. So figuring out which known converging function to use really just requires intuition. Now, this of course brings up the question, how do we know which functions converge? Like, what are the known converging functions? Well, for that, I'm going to introduce the p-test. So, if we have 1 over x to the p, mathematicians have proven that if p is less than or equal to 1, then 1 over x to the p will diverge. However, if p is greater than 1, then 1 over x to the p will converge. And as you can see over here, in our 1 over x squared, our p is 2, and 2 is greater than 1. As such, this is a known converging function. Now, we may need to get a bit creative with our converging or direct comparison test, because it is possible that our known converging function may actually be smaller than our testing function for certain values of x. But as long as at the infinitieth term, our known converging function is in fact larger than our test function, then the direct comparison test for convergence still applies, and our test function will still converge. So it's alright if for certain values of x, our converging function is smaller than our test function, as long as it eventually gets to this format. Now, this shows convergence, because if the larger function converges, then of course the smaller function must also converge. However, if the larger function diverges, that doesn't tell us anything about the smaller function. So there is another direct comparison test for divergence, which is essentially just the opposite. So we need to show that f of x, which in this case is our known diverging function, is always smaller than our test function. So this way, if a known diverging function, which is smaller than a larger function, and if the smaller function diverges, then of course the larger function must diverge. Now, for the integral test, what we do is we take the integral of the function we're testing, t of x, with respect to x, and then you go from your starting point of your series, which in the case of power series is 0, and you go from there to infinity. Now, if when you take the integral, your answer turns out to be infinity, like you get that as your answer, then the series diverges. However, if your answer is not infinity, i.e. it's some finite number, then your series converges. Now, I would like to point out that if your series converges, the answer you get for your integral is not necessarily the sum of that series. So i.e., taking the integral of a function is not a replacement for taking the sum of a series based on that function. So you still have to take the sum. I would like to point out that while integral test might seem easier, there are certain integrals you can't do. So integral test is in general an easier test to do for convergence, but direct comparison test is more robust. Alright, so let's say we have the power series where we have -1 to the nth, and that's somewhere in the power series. It doesn't have to be in this exact form, but it's somewhere in there. And then that is times u sub n, where u sub n is the rest of the power series, i.e. the rest of the coefficient, and then times x minus a to the nth. So if we assume that this is our power series, then we need to use the alternating series test to determine convergence. Because you'll notice that each term will change sign, i.e. the first term will be negative, the second term will be positive, and so on, flipping back and forth between those. Now, to test for this, there are essentially 3 subtests we need to do. Now, the first one is we need to show that u to the nth is always positive. Now, this is pretty easy. Really, you just need to check whether or not there's a negative in u to the nth. Keep in mind, it can't be a negative like this, because that just goes along with the alternating series test. So we ignore the -1 to the nths, if there are multiple of them, and just see whether or not the rest of it is positive. And again, you can really determine that whether or not you see a negative sign in there. But most often, they're going to be positive. Now, the next test we need to show is that it is always decreasing. And so the way we might go about that is by showing that some term over the next term, and that is less than 1. So what this means is that the next term is larger than this first term. So if you can show that at least eventually the series starts decreasing and continues to decrease, then that is the second condition we need to check for an alternating series test. Now, the third thing we need to check for is that as the limit as n approaches infinity of u to the n of u sub n equals 0. So we essentially need to show that our power series goes to 0 when we get to our infinitieth term. So if we can show these three things to be true, then our alternating series will converge. If one of them happens to not be true, then it diverges. Now that I've discussed power series convergence, I'd like to go over some of the potential manipulations we can do to a power series. And to go along with that, I'm going to write out the first few terms of a general power series. Now our first term is our 0th coefficient. Now I don't write x minus a along with that because we're taking that to the 0th power, and anything to the 0th power is 1, so there's no point in writing x minus a. Now next, we have c sub 1, which is our first coefficient, times x minus a. And that is to the first power, but there's no point in writing that exponent. Now after that, we have our second coefficient times x minus a squared, and then we keep adding on terms like that all the way up to infinity. So this is the expanded form of our general power series. Now, as for some of the manipulations, we can add or subtract pretty much anything. So if we wanted to add or subtract a constant, we could. We could even add or subtract an entire another series if we wanted to. Now, the same general thing goes for multiplication and division. We can multiply and divide pretty much anything. So for example, if I wanted to multiply our power series by x squared, I could simply tack on an x squared term to each of these terms. We can even multiply two series together, however that gets a little messy. If you're familiar with the FOIL method for binomial multiplication, it's kind of like that, except instead of multiplying together two term polynomials, multiplying together two infinite term polynomials, which makes the distribution annoying. In fact, it's actually impossible because we have an infinite number of terms. So when you're multiplying together two series, what you do is you calculate the first few terms of that, and then use those first few terms to try to derive a new series. So essentially when we want to multiply two series together, we pretty much have to create an entire new series. Now, we can also take the derivative or integral of our series. So, for example, if I wanted to take the derivative of our power series, I would go through each term individually and calculate the derivative of each of those terms. And that would give me the derivative of that power series. And I do the same general thing with integrating. But, nevertheless, hope you enjoyed it, hope you learned something, and see ya.